Okay, so today we have the pleasure of having Stefano Olla from Paris Dauphine, and he's going to talk about quasi-static hydrodynamic limits. Thank you, Stefano.
Thank you, Hubert, and I'm very sorry not to be in presence there. I miss a lot Brazil, and I hope it will not take too many years to be able to be back there. And so this want to present some line of work that I've developed first with Anna de Masi, and then with Lu Shu and Stefano Marchesani. And it concerns what we want to define as quasi-static hydrodynamic limits. So these are like a hydrodynamic limit, but they happen in a different time scale when the system seems globally in equilibrium, but there are some exterior parameters that change slowly, and so this global equilibrium change in time. So this is the main inspiration. I mean, this Oscar Lanford wrote some before. He died, unfortunately, some years ago. But in the last years, he was writing a book on mathematical statistical mechanics, was the title. Never got published. In fact, the notes were in his web page in Switzerland, the ATH, and has been taken down. Fortunately, I've been able to make a copy before the website of Oscar was taken down, and it's a very nice chapter on thermodynamics. And I like this phrase that I found in that chapter that for me is very inspiring in this philosophy. And it says that the idea that when constrained on a thermodynamic system are varied infinitely slowly, the system traces out reversibly a path in the space of equilibrium states is at heart of most applications of thermodynamics. It seems to me that is at least as fundamental and at least as deep as the first law itself. It is to be emphasized that this is not something which is deduced from more fundamental ideas. It is rather an important piece of physical intuition, or if one wants, an axiom of thermodynamics, but one which is very hard to formulate precisely. So our idea is just we would like to obtain this thermodynamic transformation, the one that you study in thermodynamics, the reversible one, the one you construct this Carnot cycle, the isothermal, the adiabatic, where you read in the book of thermodynamics, so you move so slowly, you change very slowly, the system is always in equilibrium, but the equilibrium change in time. We want to obtain from the microscopic dynamics. Instead to try to obtain the hydrodynamic equation, try to obtain directly this thermodynamic transformation. So the quasi-static scaling limit corresponds to a change of the boundary parameters, that could be tension, temperature of the thermostats applied on the side, density of particles in the reservoir, which is on a time scale that is slower means larger than the typical equilibrium relaxation time scale of the bulk dynamics. So we are interested in bulk dynamics with conserved quantities. So we'll take, since there are conserved quantities, will take time to relax to equilibrium. So this is very large quasi-static time scale. The system is always very close to the global equilibrium, corresponding to the time-varying parameters applied at the boundaries. But so this is reformulating what Lanford was saying, that the existence of this quasi-static transformation should be seen as another thermodynamic principle that we want to obtain from the microscopic dynamics. Oh, this is not good. Okay, we want to go beyond transformation from one equilibrium to another, and we want to study quasi-static transformation between non-equilibrium stationary state. I mean, usually thermodynamics talks about the quasi-static transformation from one equilibrium state to another equilibrium state, but we also can do it between non-equilibrium stationary state. And I'm saying the inspiration of this was certainly Lanford, but also Claudio with René Lazini. I think there was years ago a seminar of Claudio, was really inspiring about that. Where they apply these ideas to obtain certain approximation in the fluctuation theory. Okay, so with Anna, we have developed these kind of ideas for our many systems, but today I just want to concentrate on systems that everybody, I think most of you are familiar, which is the simple exclusion. And first we talk about the symmetric simple exclusion. So this is the system where it's very easy to define non-equilibrium stationary state. So this particles just move in the lattice. Just let's take one dimension. Let's really work in the most simple possible framework. The particle moves symmetrically with the exclusion rule. So there is a parameter gamma, and then there is a time scale. As you see, the time scale now is n2 plus alpha. The typical time scale is n square if the system is length n. This is a diffusive space-time scaling. Since it's symmetric, you have to rescale time like n square. We want to look now at the time scale which is longer, 2 plus alpha. This is longer time. This look at the time scale. At this time scale, the system tends to be in equilibrium. But the boundary, there are boundary rates. Here there are particle that jumps in and jumps out, jumps in with the parameter rho minus t, and out with the parameter 1 minus rho minus t with this intensity. So they try to fix the density on the left to be rho minus at time t, and on the right rho plus at time t. But this happens at time t. See, the time t here is not rescaled. So this you should think t as just already a macroscopic time scale. So when you look at the system, this is the generator of the system. It's the generator for the exclusion. And then there are the boundary rates. The boundary rates changed at this macroscopic time scale, which is the operator you see, just the generator already multiplied by n2 plus alpha. So typically, for large n, you should see the system, if for example, rho minus is equal to rho plus, you should see the system at that density fixed by the boundaries. Of course, now if you choose rho minus different from rho plus, there will be a flux of particles inside. So the system will be in a quasi-stationary state, but that changes in time continuously. So this is the, let's say, first look at the symmetric case. The symmetric case, things are very simple. It's just an exercise.
Claudio,
yes.
I have a question. In your notation, eta 1 is and eta n, they have the configuration where you have flipped the.
Yes, sorry. Yes, this is the flip. This is particle. Eta 1 is means the configuration where the first particle has been flipped. So that means if it was 1, if it is occupied, is empty, and if it is empty, is occupied. So if it is 1, is 0. If it is and if it is 0, is 1. So this means just the flip of the first particle. This is the flip of the n particle from 0 to 1 or 1 to 0. And eta x plus 1 is just exchanging the occupation side with x and x plus 1, which is exactly what happened inside the bulk. So I don't need to put any intensity here, because in the symmetry case it's just, I mean, if you consider the exchange, you can consider the jump, the exchange between a site and an empty particle and an empty site, or the other way around. Okay, it's just about the definition. Yes.
What is the time scale at which rho varies? Is it 1?
Yeah, you see, rho. This is exactly. I mean, just take t as a macroscopic time scale. We have already
it's
applied
already
the generator by n to the 2 plus alpha.
Okay.
So we are looking already at the time scale, the larger time scale beyond the diffusive time scale. So you typically expect the system to look in a kind of a stationary state, but it's not, because eventually I'm changing the time in this scale. So what happened is that, I mean, you can, it's not difficult to prove that if you look at the empirical distribution, here it means the empirical distribution of the occupation, so this empirical density, these converge to in some weak sense, to a function rho bar yt, change in time and the change in y. If alpha is equal 0, we are in the usual hydrodynamic scaling limit, so you get the linear diffusive equation with the boundary condition given by the densities, and this can change in time. But if I take alpha bigger than 0, this is the quasi-static hydrodynamic limit, then I get that the profile has to be just an equilibrium profile, but where the bound, so that means just a Laplace, second derivative of rho equals 0, so it must be just a straight line that goes from rho minus to rho plus. But rho minus rho plus change in time. So this is the quasi-static equation in this simple case. And I mean, this paper in GSP in 2015 with Anna, where this is also actually proved us in a nonlinear system where things are a bit more complicated, or in chain of oscillators and so on. But today I want just to talk about simple exclusion. Okay, so once you have such quasi-static dynamic limit, you can also ask for large deviation. No, sorry, before, let's see what happened to the current. So because if alpha, if rho minus and rho plus are different, of course these are a quasi-static transformation between non-equilibrium stationary state. Okay, you can see that. And so there will be a flux of particles. So let me call j tx the number of jumps from x to x plus 1, that number of particles that move from x to x plus 1 at up to time t, minus the one that moved from x plus 1 to x. So this is the total current up to time t around the point x, around the point jump x and x plus 1. And of course you expect at this time scale to have n1 plus alpha, typically n1 plus alpha particles. This is probably not totally obvious. Since it's symmetric, the time scale is n2 plus alpha. Since it's symmetric, you get fluctuation and it's 1 over n. And then the alpha is the correction that you must have in this time scale. And then you can prove that you converge, this current converge, always the same, to some constant current. At this, after n goes to infinity, you should see the conservation law, you should see just a current that change eventually in time, but change in time because you are changing the density at the boundaries. Yes?
So a quick question. So why is alpha not alpha divided by 2 in this formula?
Well, if you do the calculation, it's alpha. But it's because it's induced by the gradient of the densities. Now it's maybe a bit, it could be confusing because you can see that 2 plus alpha. But if I haven't done stupid mistakes here, I believe that alpha.
Yeah, I think the gradient of the density is 1 over n. So you have the time scale divided. Well, you have 1 over the time scale multiplied by n or something like that.
Yeah. Okay, perfect. Thank you.
Thank you, Bert. Remember better than me. Yeah. But, okay, then you have this current that is established at every time t. This change in time t because, again, the densities change at the boundary. And you can compute it as exactly the current. This will be the instantaneous current. This will be constant in y. And this is equal to rho minus rho plus, the difference of the gradient integrated in time, because this is the total current up to time t. Okay, and this is very rigid. It's very hard to change the current in this time scale. But you can ask, now we can look at the large deviation, you can ask, well, what's the probability to see some different current? To have, instead to have that this current is just some other value of j, some other current there, but it must be constant in space. You cannot see it's very hard to see a large deviation where you violate the conservation law. Basically, the conservation law really imposes you that gives you a rigidity in the current profile, and then you can ask also what the probability to see a different profile than the quasi-static one. And all these probabilities up to time t, all this probability can decay in time, like e to the minus n1 plus alpha. Again, the quasi-static thing appears there, and the rate function I has this explicit expression when it is finite, and then usually you have a variational formulation of the rate function, but it looks very similar in a way to the rate function you find for the stationary state of Derrida and Bodinot. But in fact, it's conceptually different. One of the different conceptions is that here you can see that the current cannot change in space. It has to be a constant function in space. Just you can ask what the probability to see some global different current in time, and so this will be the rate function satisfy the Gallavotti-Cohen fluctuation relation. So if you ask, if instead of J you want to see a current minus J, the relation is just given by this expression here, and there's a log of this. You can see this as a free energy report of the free energy of the density at the boundary.
I have a question, Stefano. So
yes.
when you say that, okay, in your rate function, J does not depend on space. Does
Yes.
that mean that if you want to approximate something that depends also on space, you would have to
It's
consider...
much smaller. Will be much. Suppose I'm asking. In principle, JTY may depend on Y, and then I can say, well, what the probability of JTY is some J, some function different with change in space. That would impose that there will be a big accumulation of density on one side and the other side. The conservation law makes it very rigid, and this time scale cannot happen. The probability will be enormously smaller.
Okay. So I is plus infinity in that case.
Yeah, I is plus infinity in that case. If I want to see something changing in Y, and then you can do other funny calculation that. Suppose you want to compute, you take the same density profile, but you want to see, invert the flux. You want to see particle moving the other side. Then you can see that this the cost will be the sum of the two relative entropies of rho plus with respect to rho minus, plus rho minus with respect to rho plus. I don't know. I don't have a particular physical interpretation. It's just an interesting fact that if I just want to see the same profile, but just invert the current, just see particle moving with the same intensity, but in the other direction, this will cost the sum of the two relative entropy. So it's like I have to change in the equilibrium at the boundary. Okay, so this is all we know about the symmetric case. This is in a paper, large deviation, a paper in Anna's Poincaré, always with Anna. But things get quite interesting in the asymmetric simple exclusion. So we take now the open asymmetric simple exclusion. So now particle move asymmetrically. Let's say that they jump with probability p and 1 minus p. Right with probability p and left with probability 1 minus p. Just to fix ideas, let me take p bigger than 1 minus p. So we have a general tendency to move from right to left, just to fix ideas. And then we have reservoir of particles. The general situation, we have particle jumping in with rate alpha, jumping out with rate gamma. This is a standard notation. Beta out of on the right, and delta they come in from the right. Okay, so this is the open asymmetric simple exclusion, And of course, you can here there are 4 parameters: alpha, gamma, beta, delta, plus there is a parameter p, which is the asymmetry. If you make one of the first person who considered this open asymmetric simple exclusion was Liggett. This is a seminal article of 1975, and he makes a particular choice. Alpha is equal p rho minus, gamma 1 minus p rho minus, 1 minus rho minus, and a similar choice for beta and delta. So we call these Liggett's boundaries. The idea of Liggett's boundaries is that they basically make the best approximation of the infinite system. So here looks like there is something with density rho minus on the right, and here on the left, and here on the right looks like density rho plus. And imagine that you have the system outside in equilibrium, but still asymmetric, and this is exactly the rate of like particle will jump in if the system outside here with the density rho minus, and same thing with rho plus here. Okay, and the reason why Liggett chose this boundary condition was that he wanted to study the infinite system, infinite asymmetric simple exclusion, and with asymptotically different density rho minus and rho plus. And this was the best possible approximation. So it's basically mathematical reason that you typically Liggett and many other people worked with these boundary conditions, and but physically you see that they are not reversible. In the sense you're choosing the rates. The rates depends on the asymmetry on the bulk. Okay, so these are the Liggett boundaries, but we want to consider also other possible boundaries, which we call reversible reservoir boundaries, which are essentially the same boundaries we were considering. For the symmetric case. This really means that we are putting a reversible reservoir of particles with density rho minus on the left and rho plus on the right. So these are exactly like before. So these are 2 different class of boundaries that you can choose in this asymmetric simple exclusion. And of course, you can study also the more general case. But these are the. So I would think these are kind of more physical boundaries, but these are certainly easier to deal mathematically. And then it's interesting to understand what kind of boundary condition you obtain from these microscopic dynamics in the hydrodynamic limit and in the quasi-static limit. And let's say for Liggett boundaries, there is a result by Christophe Badoran. He extended the hydrodynamic limit in the infinite volume was proven by Rezan-Callot, and Badoran made the extension to the open case. So you have the extension, the open case with the Liggett boundaries. Then you have that the density field converge in a weak sense to the L-infinite entropic solution of the Borges equation. The Borges equation with a given boundary condition. Now, if this is the first time you see this is such a very non-trivial statement, because you have to specify what does it mean that an hyperbolic equation has boundary conditions. Since hyperbolic equation can develop shocks and develop discontinuities, it does not have, it always looks overdetermined when you want to put boundary condition on both sides, unlike the diffusive equation. So the boundary, so there are always some boundary layers that forms on the boundary, and the way to describe these boundary layers have to be somehow ergodic, entropic in the sense of entropy of a definition of the entropic weak solution. And the boundary conditions are satisfied in the sense there's a paper by Bardos, Leroux, and Delec 79, which is good for bounded variation solution, and for us important generalization of Otto for L-infinity solution. L-infinity solution are important in the sense that typically a hydrodynamic limit, in a hydrodynamic limit you don't have bounded variation. You don't obtain bounded variation solution. You don't have bounded variation estimates, but only natural infinity estimate, like certain in the exclusion process. You know that the limit has to be bounded between 0 and 1, but a priori you don't have bounded variation solution. So I will go back to say exactly what and this result is want to stress the fact that this is for Liggett boundaries. For reversible boundaries, as far as I know, was an open problem until maybe a week or two before. But I mean, Lu Shu came out with a paper now where you can deal with the general boundaries, obtain the same result. But I mean, as I will say before, you have to speed up the boundary in a proper way. Okay, so now what is the quasi-static limit for, in the case of the Liggett boundaries? We just speed up now time, like n1 plus alpha. So n was, as you see also before, n was the hyperbolic time scale. Now instead of n squared to obtain such Burger's equation, you have to speed up like n, because the equation, the natural space-time scaling is the hyperbolic scale, space like time. Now we look at a larger time scale, 1 plus alpha, so we are beyond the hyperbolic scale. For technical reason, we have result for alpha bigger than 1 alpha. This is technical. I think there's no, just should be true for any alpha positive, but unfortunately we prove it only for alpha bigger than 1 alpha. Probably we can improve now. But then the density profile converge at these times, quasi-static time scale, to what we call the entropic L-infinity weak solution of the quasi-static equation. What is the quasi-static equation? Well, it's an equation in which current has to be constant. So J of rho is 2p minus 1 rho 1 minus rho. This is the macroscopic current when you have the density rho, and has to be constant in space. This is certainly a good situation, a static, good stationary situation, but the boundary condition have to be rho minus and rho plus, and again the boundary condition have to be satisfied in the Otto sense, and I will explain again what this doesn't mean that I mean rho bar will be typically, you see, I mean we see how this is, what does it mean an entropic L-infinity solution of this equation. Of course, it has to have some discontinuity necessarily if rho bar is different from rho. If rho minus is different from rho plus, it cannot have just a continuity, so it must have some discontinuity, some shock somewhere. That could be or at the boundary or in the middle. So the boundary, okay, this is something I said, that this should be true for any alpha. And we have the result also for reversible boundaries, not the Liggett boundaries, but for reversible boundaries, you have to speed up also you have to speed up three things. You have to speed up inside, you have to put a lot of symmetric exchange. Basically, you should consider to our asymmetric simple exclusion, we add some symmetric exchange inside. We increase the diffusion of the system, but small enough to not make arise any diffusive term on the macroscopic. So sigma should be large, sigma n should be large, but not too large. So it should go to infinity, but it should, sigma n over n has to go to 0, so that there is no diffusive term appearing from the bulk. But also the boundary terms have to be speed up. And this because if you just take reversible boundaries, the system doesn't really like this reversible boundary. It's not clear what will be the boundary condition if I don't speed up the boundaries. But speeding them up with sigma tilde n and other, then they impose to have the right boundary condition, again in this weak entropic sense. And again, we obtain in that case this equation. So you have to do such speeding up of the.
I have a small doubt about what you say, because you've written that sigma n multiplied by n to the 1 plus alpha should go to infinity, but you said something stronger, that sigma n itself should go to infinity. So which
sigma
one?
n should go to infinity. Okay, what is important? Sigma n over n. Don't know if I mess it up here. We have already n1 plus alpha multiplying outside. So I have that sigma n1 plus alpha. Of course, this goes to infinity. Sigma n itself has to go to infinity, but sigma n over n has to go to 0. So basically, you want sigma n that should not grow like. I mean, should go. Now I don't know. It should be n like n1 minus alpha, something like that. I'm not able to do the calculation here, but there is you have space here in between to. The important thing that you speed up. You put some symmetric part in the generator fast, but not so fast that no Laplacian should appear in the macroscopic.
Okay, but it's always faster than the asymmetric part.
It's always faster than the symmetric part.
Okay, thanks.
So this should give you more viscosity at the microscopic level. Give you more viscosity, and you see why this is important soon. So
hi, Stefano.
Yes.
Sorry. Do you require alpha to be smaller than 1 here for the symmetric part?
No, alpha is fixed here. Alpha is fixed here. It's a technical requirement that has to be bigger than 1 alpha. Why?
Because if alpha bigger than 1, then the diffusion part you will appear, right?
If alpha is bigger than 1, yes. Yeah, you don't want to do that.
So you
see, doesn't matter, because when you speed up alpha, you can also take alpha bigger than 1. You speed up as the symmetric part, but then you speed up as the asymmetric part. If that will become very dominant, and you will be anyway.
Okay.
The effect of the Laplace is still be relevant. You will be really in the quasi-static case.
Okay. Thank you.
But the alpha bigger or smaller than 1 will make a difference when the shock is inside. I will say something later on. There are situations in which alpha bigger than 1, alpha less than 1 are actually different.
Okay, thank you.
Okay, so then I want to mention a fact that very recently Lu Shu, basically speeding up, putting alpha equals 0, but speeding up the boundaries and the symmetric part like that, he obtains the hydrodynamic limit with this more general boundary condition. And in fact, this proof, unlike the proof of Badoran, is very much based on the proof of Rezan-Kalou. And with the Liggett boundary condition, they use strongly coupling properties of the simple exclusion, while this proof here doesn't use at all any coupling, so nor attractiveness of the system. So it could be a proof that can be generalized also to non-attractive dynamics. And it's very much inspired on the technique developed by Joschka Fritz and using compensated compactness on the microscopic level. Okay, So I should say now finally, because I'm talking something which I haven't described yet. What is an entropic L-infinity weak solution of a quasi-static equation? So this is a quasi-static equation. What is the entropic weak solution? So we wrote a paper about this because apparently there was no literature on mathematical literature, and they accepted it in a journal of analysis. So I believe that we were right not finding such object before in the mathematical literature. So the entropic solution is defined this way. Take the Burger's equation. This is actually good for any concave flux. There's any concave flux that between 0 and 1 or 0 any other particle, and then you have some convex flux defined this way. Then you have you look at the Burger's equation corresponding, or the scalar hyperbolic equation, where you have boundary condition defined in the Otto sense, or I will explain again about that. And then you send epsilon to 0 to this equation that it kills the derivative part. This is the quasi-static limit at the level of the hyperbolic equation, and the limit will give the solution of this entropic solution. Of course, you have to prove something that such solution converge to the entropic solution, to something. But in this case, so this basically is the definition of the quasi-static hyperbolic of the entropic solution. It's like a viscous. You take an entropic solution which is already obtained by some viscosity limit, and then you still send rescale time in such a way that the time derivative part goes to 0, and you obtain the solution you obtain some object which is like that. And actually, you can compute it explicitly. This solution, they are easy because they're related to the stationary situation when things don't change in time. This is where this you define thing where these densities at the boundary are changing in time, but things like this quasi-static solution is just determined by the boundary condition. And they're defined the following way. There is a critical line, like suppose this is J, this is the current, the graph of the current, and now for any density rho here, there should be another point rho star which have the same density. In the case of the Burger's equation, rho star is just 1 minus rho, of course. And then there is a critical line in which rho star is equal minus rho, and rho star are just symmetric. Suppose you are not in the critical line. If you are not in the critical line, you have an explicit expression of rho bar. So rho bar, the solution of the quasi-static equation, should be or the density on the right or the density on the left, and that depends if the density on the left is less than the maximum of the current, and rho plus is less than rho minus star, or the other way around. So this could be you can figure out how this is defined, but this looks a bit complicated looking like that. But there is actually there's actually a nice characterization. I will come soon. If you are not in the critical line, the solution is unique. So basically, you have a discontinuity which is or on the left or on the right, but cannot be in between. In the case in which you are in the critical line, then there are infinitely many solutions, and because you can have basically the situation where there is a shock in between, so you can have rho minus here, rho plus here, and there's some shock in between. And this can happen only if the boundary conditions are in the critical line. And of course, you can have many positions of the shock. For any position of the shock, you have a different quasi-static solution. So you don't have uniqueness anymore of the quasi-static solution. We'll see what we can say about that. But otherwise, you can characterize it in terms of the current. So the entropic solution maximize the current in the downhill case and minimize the current in the uphill case. So that means if the density on the left is bigger than on the right, that's the downhill case. I mean, the gradient of density goes in the same direction as the asymmetry. Then you have always have that the solution maximize the current. In the other case, when you go uphill, so you are working, the gradient works against the drift of the particles, then you minimize the current. This between all possible values between rho minus and rho plus. So you choose rho minus or rho plus, depending if you want to minimize or maximize. And this is actually the same thing that happens when you study the stationary state. It's just the same thing happens in the quasi-static. In the quasi-static stations, the only thing that now everything changes in time. Okay. And so I still have to say, what does it mean? How this boundary condition were satisfied from before solving the equation. How do you get this explicit solution? Well, you have to go back to the definition of entropic solution. When you give an entropic solution of a hyperbolic equation, you introduce the Lax entropy pair. This is a function, a convex function S, and this flux Q. These are C2 function, but S has to be convex. And rho is an entropic quasi-static solution. This is like the definition of an entropic solution of a hyperbolic equation, but is now only the flux is present. So that means the flux of the entropy integrated against the gradient of a function phi, and the function phi is positive. Test function phi positive, this has to be bigger than 0. So this is basically said we have kind of a positive production of entropy where S is one of any convex function here is one entropy. Then this is the usual concept of entropy pair that you find in the classical literature for hyperbolic equation. But then there is the boundary entropy pair. This is something that Otto used to characterize the boundaries. So a boundary entropy pair is the now function of rho and W, Q and W, and this is the entropy and this is flux. As a function of rho has to be like a Lax entropy pair. But furthermore, they have, so this is the relation that the gradient of rho should be J prime, gradient of S. It's the same relation as this one, but respect to rho. But respect to W, SWW should be QWW should be equal to 0. And also the gradient respect to rho or to W when computed in W has to be equal to 0. And then this characterizes the boundary conditions. That means this characterization works also for L infinity solution. You take the L infinity solution if the limit as R goes to 0 of the flux between rho bar and the boundary condition rho minus integrated against the function beta positive is negative. This has to be satisfied by rho bar. And this is the other side. This is the other condition for the other side. Morally, this says that entropy has to flow out of the system in the right direction. This, if you look at it physically, and if you take the physical entropy, has to the evolution has to not increase the entropy, but decrease the boundary condition have to decrease the entropy, not increase it. Okay, these are what's called the Otto boundary. So this is what I explained before. And these are equivalent actually to the Bardos-Leroux-Nedelec boundary, which they are more explicit in terms of what the left and the right limit if this quantity exists. But this is for make them exist, you need bounded variation solution. Actually, the whole thing looked like a bit academic at a certain moment, because after the work of Otto, there were works of, I don't remember now, the French mathematician, that I don't remember now the name, but that proved that if you start with L infinity initial condition, these hyperbolic equations are regularized enough that you immediately find yourself the unique solution. L infinite solution is actually a positive time is of bounded variation. So you can actually take this the Bardosne-Derune-Delec boundary condition seriously, in that sense that they will, at positive time they will be satisfied, even though the equation that you obtain isn't there. So this is I want to say two things more. What time is it? Okay, I want to say two things more. One is about the proof. I don't want to go into the proof, but the hardest part, it's a bit of a paradox, but the hardest part is to prove that we have a quasi-static evolution in equilibrium when rho minus is equal to rho plus. It will be totally trivial if they don't change in time, because you are in the stationary state. Actually, the stationary state, you know explicitly, you can prove everything. But when time changes, you have actually to prove that things remains close to the global equilibrium. That's the hardest part. And in order to prove this, we need to prove that when rho minus is equal to rho plus, there is the entropy fluxes are negligible. You can define an entropy fluxes on a macroscopic level, and you have to show that is actually negligible in the limit as n goes to infinity. Then there is a relatively standard coupling argument that shows that the support of the Young measure associated with the density profile is concentrated asymptotically to the interval rho minus and rho plus. So when you take rho minus and rho plus different, you can couple to the equilibrium situation, and this is a relatively standard coupling argument that Pablo will do it with blindfold. And then the same coupling argument actually showed that the limit current satisfies the variational principle. That's the variational principle is the one that maximizes currents when in the uphill case and minimize current in the downhill case. And the Young measure support concentrates then on its explicitly known entropic solution. And we use the fact that we know explicitly what the solution will be of the quasi-static equation. Now, I have to confess that all this works outside the critical line. When the shock is there in the critical line, things are a bit more complicated. Let me consider now, this is I would say it's still at the level of conjecture. We have no proof of this, but that's what I believe will be true in the critical line. The critical line, as I said, we don't have uniqueness of the equation. So what we should get, because we don't have uniqueness of the quasi-static equation. This is the case where rho minus is equal to a certain value rho, and rho plus is 1 minus rho, where rho is less than 1/2. So we have an uphill situation. This is rho minus. So maybe I put here. This is rho minus. Then at a certain moment there is a position of the shock, and then there is rho plus. So, of course, since rho minus is equal to rho plus is equal to 1 minus rho minus, the current is the same, and that's why you can have a quasi-static situation with the shock in the middle. And the current will be constant everywhere, constant in space. Now you have that the shock, you know that it's going to move in a diffusive way. There are works of, I think Pablo was involved in this, Anna, Enrico. When they studied this movement of the shock in the infinite volume, the shock moved diffusively. If it move diffusively, so you expect that this is the case when alpha is less than 1, it doesn't have time to move when you rescale space and time, because you should look at you're looking at this it's a larger time scale than the hyperbolic scale, but it's shorter than the diffusive scale, so the shock doesn't have time to move. So whatever shock you have at time 0, you have a shock at time 0, which will be in a certain position x, they call it x0, and then you have here rho t, and here you have 1 minus rho t on the other side, and you have a certain position. Then at time change, you can have that these two values change, but the position of the shock should stay there, never moves. So basically, you have you still should converge to this particular quasi-static solution with the shock always there. It's conjecture, cannot prove this. This will happen when alpha is less than 1. When alpha is bigger than 1, then we are looking beyond the diffusive time scale, and the limit profile should be random, should be anything. You don't have a limit, you don't have a large number. In a sense, you can find any position of the shock uniformly distributed in between 0 and 1 will be a possibility. So and you just get a superposition of all these random profiles. You get a random profile. So the limit profile will be random in this sense. You really feel the fact that they have no uniqueness in the solution. When alpha is equal 1, this is a critical case in which you have non-quasi-static behavior. You will see the shock moving at that time scale. So you will see some profile that depends on the initial condition. And so I say this is a non-quasi-static behavior, because quasi-static would mean that you don't see it really evolving in time, and instead you will see a profile that is evolving in this time scale with something that depends on the initial condition. But these are very kind of a vague conjecture of what we prove, and something that we hope to prove in the future, that something like that can happen in the critical case. So, just to conclude, the other possible evolution, we would like to look at what happened to the large deviation, the quasi-static dynamic limit. We know that there is, for the accept, there is in the infinite volume or periodic boundary condition, there is the Jensen-Vardan large deviation functional, which says that compute the deviation. We have to look at how much the deviation produce entropy in how much entropy is produced by the deviation. That to give the Jensen-Vardan large deviation function. It gets a bit more complicated here, because the boundary condition, at least in the leaked case, the boundary condition will the large deviation function will depend also on the boundary condition. The change of the boundary condition will contribute in the large deviation, not in the other case. And then I'm very interested in studying the quasi-static limiting when multiple conservation laws happens, like a chain of oscillators where you have conservation of energy and conservation of volume or of momentum, and then you want to see adiabatic evolution. Quasi-static adiabatic evolution, where energy is conserved in the evolution. Okay, then I think I can stop here, and we have some time. But, I've finished what I wanted to say. Thank you very much for your listening.
Thank you, Stefano. So now it's open for questions. So I think, given the number that we are, it's reasonable. You can just unmute yourself and ask your question if you have a question.
I have a question. Stefano, so you talk about when there is a shock, no? That you...
yeah, we talk. I mean, that's a conjecture. We don't have
yes.
Conjecture based on your. I still think you were involved in this, of the diffusion of the shock, no?
I did some things, yes. So I see that if you are subcritical, you are stopped and critical. Maybe you see a uniform distribution of the shock, probably. Or in the supercritical, you should be at each time you see a different uniform position of the shock, I guess.
I mean, you mean when alpha is
if
bigger?
You are alpha bigger than 1, yes.
Alpha bigger, yes.
And
I mean, if you
equal to 1,
you average out, you should look like the stationary states and linear profile. But of course, here
but
you
jump to another because it's too fast.
Yes.
Yeah. But you didn't say anything when you have rho minus bigger than rho plus, when you have the rarefaction fan, or did you?
No, rarefaction fan, that's rarefaction fan, that's included in the previous case. Because when you have rarefaction fan, you have a quasi-static solution.
Yes, but what is the density? It's constant. It's constant.
It's constant, equal m. Okay, the rarefaction fan. Let me go back to the explicit solution. Will be this. In the rarefaction fan, if they are, you see, rho minus bigger than m and rho plus less than m, you get the maximum current.
Ah, okay. The maximum of the two. Okay.
No, the m is the middle.
M is a 1/2.
Yeah,
1/4.
1/2. Yeah. No, m is 1/2, the density. The current will be 1/4. J 1/4 will be the current. So 1/4 is the maximum current, and you get just the maximum current case. I mean, that means you have rho minus bigger than m, rho plus less than m, you get the maximum current. You get, which is what you see also in the stationary state. Same thing.
Okay. This is already proven by
just changing in time, but in fact the profile will not change in time as long you keep rho minus bigger than m and rho plus less than m. You will have a constant, not even changing time. You just always get the maximum current profile. And that will correspond to the rarefaction case.
I see. Thank you.
Yeah.
So I have a question. So in this quasi-static transformation in which you speed up the evolution inside, could you study the difference between what you observe and the stationary solution? Because you won't be exactly, you'll be very close, but there will be a difference between your distribution and the stationary distribution at time t if you fixed that chemical potentials at the boundary.
You mean the fluctuations?
Not exactly. It's like a first order correction to your equations. More in that spirit, not in the spirit of fluctuations.
Yeah, okay. No, we didn't look at that. We didn't look at that. I mean, this is more what your motivation in looking at this quasi-static.
Yes.
In your paper with Jona and the others, you look at the quasi-static evolution because you want to look at the correction of this. But no, we didn't look at that. No, that's probably in the symmetric case, one will get something similar to what you have found with Jona and Lorenzo. In the asymmetric case, I think it's a very difficult problem. As usual, all this kind of correction in the asymmetric case is very difficult. Even to make a guess. But I guess in the symmetric case, I believe one gets something similar to, in the general case, to what you already studied with Jona and Lorenzo and Davide.
Yes, but in the asymmetric case, it was exactly what we studied, though in higher dimensions, right? The corrections of the asymmetric. Yeah.
Yes.
I have
I must say that I really didn't look at this problem of the first order correction, even though your talk a few years ago was inspiring for all this, but it didn't go in that direction. No. They don't have an immediate, for me, they don't have an immediate thermodynamic interpretation, these corrections. So that's why I still to understand that.
Okay, so Stefano, I had a question about this conjecture on one of your last slides about the case when alpha is smaller than 1. What is the intuition behind this thing that the shock wouldn't move?
Why alpha less than 1?
Yes.
Well, alpha less. Look, I mean the shock. The shock wants to move diffusively. So at a time n1 plus alpha will move on something which is of the order n 1 plus alpha over 2 distance.
But since rho is changing, okay, so I think this is not what happened, but maybe you can have some conserved quantities somewhere. So imagine that if the global density was conserved, for instance, just changing the boundary condition would kind of force, I mean, conserved on this time scale, just changing the boundary condition would change the position of the shock. Right?
Well, okay, the conjecture relies on the intuition that comes from the infinite volume that the shock moves diffusively. Now you are saying, oh, maybe the boundary conditions are actually imposing some drift on the shock. Some drift toward
just
the
because of
that will confine more or a drift towards the. I don't believe this is happening, but I don't have a proof of this because this of course will change the movement of the shock. My intuition is that the shock will keep moving diffusively. I don't know. Pablo may have different. He knows better this problem than me, but.
Just this will be diffusively also with some randomness given by the boundaries, because the diffusivity in the infinite case is present already in the initial configuration. So you at the level of the diffusion is given by the initial configuration. So since here your initial configuration is finite, a part of the randomness is coming from the boundaries, but in any case will be diffusive, so you will see it frozen, as you say. You agree, Hubert?
We're talking about let's talk about Liggett condition, no?
So yeah, Liggett condition. Yes.
Otherwise, the situation becomes more complicated. Let's talk about situation with the Liggett condition. Liggett condition basically. I believe in the Liggett condition there is not much difference when you look inside the system. You don't see much difference between the infinite volume and the infinite system and the finite system. That's
okay. So if there are no more questions, I think we can thank.
Can I ask a question, Hubert?
Oh no, there is a question. Sorry. Go, Milton.
Yeah. Okay. Yes. Thank you. So this is actually it's a very vague question I want to ask because I've been looking at this. It's a general fact about the non-equilibrium stationary states. I've been looking at them and then they look efficient in some senses. Okay, so when efficiency means different things for different models. But maybe you have a more concrete idea of what efficiency would mean for the non-equilibrium stationary states, Stefano.
No, I don't. Since basically, I mean, I would like to arrive to understand non-equilibrium transformation or quasi-static transformation between non-equilibrium states, some general principle, like you have in thermodynamics, but I don't have enough. I mean, I'd like to arrive there to understanding this transformation. I mean, for example, understanding the quasi-static. I mean, what corresponds. I mean,
Yeah.
say efficiency, like I believe you think about the equilibrium case. You have Carnot cycles, no, and you have general principle of Carnot cycles. In particular, second principle of thermodynamics. You formulate in terms of the Carnot cycles. What is the equivalent statement in the for non-equilibrium transformation? If you construct a kind of a Carnot cycle with non-equilibrium between non-equilibrium states, what will be the general principle behind it?
Yeah, exactly. I imagine that it could be more efficient, no? Because this is something people are claiming that, no, in like biological systems that are typically, so you have this bacteria immersed in some non-equilibrium stationary states, and they do work more efficiently than the guys which are immersed in equilibrium stationary states. That somehow they I don't know.
Yeah, no, I understand what you mean. Is of course scales will be the point of this, and we see already from symmetric and asymmetric that in non-equilibrium scales are space-time scaling are important, while in equilibrium they don't. That's why the usual thermodynamics is something that doesn't talk about the open book of thermodynamics that doesn't talk about time scales. A book of non-equilibrium thermodynamics, a possible future book of non-equilibrium thermodynamics has to talk about space-time scales because that's relevant. And that means for certain space-time scales, probably you can make processes which are more efficient than the usual thermodynamic process. I mean, that's probably one can construct machines at a certain scale, so space-time scale, which works better than the Carnot machines and so on. I always think that when people use thermodynamics and concepts coming from thermodynamics, always forget that thermodynamics only talks about transformation between equilibrium states. And they may be applying this thermodynamics to systems that you do not have equilibrium states, and then they arrive to say things about the universe and so on, which don't make any sense. I believe a good understanding of non-equilibrium thermodynamics can eventually build up processes that are more efficient. But I don't know. This is really, we should ask, I don't know, Yona, question like that. The people that have a clear vision about. But I don't know if there is a clear vision about this.
Okay, thank you.
Okay, do we have more questions? Okay, so I think we can all thank Stefano. Thank you very much.
Thank you very much. Hope to see you in real life very soon. Bye-bye.
Bye.
Bye.